I'm sure some of you have heard the least action principle in relation to Lagrangian mechanics. Actually, this principle has played a very important role in modern physics over the past centuries, since 1900, starting from the quantum mechanics, both non-relativistic and relativistic forms, and the relativity, both special and general, developed by Albert Einstein. In particular, since 1930s, and the least action principle has been also adopted in the study of quantum field theory, including the very recent talk about the Standard Model. So it would appear that the least action principle is so fundamental that actually to some degree, people could argue that it is more fundamental than basic law in physics, such as Newton's 3 laws of mechanics. Is that true? Well, this issue has been in my brain for decades, and whenever I have time, I would love to go to more detail. Finally, I have time to do so. So I hope this talk will give you some new perspectives, if not totally surprising, and insight into this basic issue in theoretical physics. Welcome to Yong Tuition. This is a unique channel to explore and to study and share the knowledges about the basic issue in physics and beyond. I hope you enjoy this talk, so please don't forget to like and subscribe. Let's go to the blackboard. This is big issues in physics. So therefore, today, I will just give you a brief introduction or overview of what I'm going to talk. Here are the, let's just enlarge my profile a little bit. Okay, oh, I'm bigger than those great physicists. Now, these are some of the key physicists and mathematicians behind this least action principle. Among them is, of course, Isaac Newton, his rival, Leibniz, and followed by Yong and his student, Lagrange. And these two are Bernoulli and Hamilton, perhaps are familiar to many students in physics. But this guy is called Maupertuis, or Maupertuis, is a little bit obscure. But based on my study, actually, this guy is also responsible for the creation of the idea of action. And gradually, of course, we'll talk about some more recent physicists. Among them are James Maxwell, Albert Einstein, Paul Dirac. And the last two are my favorite among the recent physicists. One is Freeman Dyson, another is P.W. Anderson. And he created a field in physics, in modern physics, called the condensed matter physics. I happen to be a researcher in that field. And of course, I will explain why I didn't put the portrait of Richard Feynman and other things, other person in this list. I will tell you gradually. Let's go to this introduction. So the whole discussion will be called as in-depth discussions on the least action principle. And the big guy, the key person would be Lagrange. And however, the idea of action had been proposed, had been investigated or considered before the Lagrange. And among them are the Leibniz. So this is some of the forms of action you can find. Actually, the action idea was first discussed in the context of how to discuss the path of the light. We know the light travel in a vacuum, always go to along the straight line. So therefore, the Leibniz, Horner, Bernoulli, and Maupertuis all argued that maybe we can focus on this product and their path integral, namely the light speed c and dt. So that is the early idea about action. Of course, everyone who studied analytical mechanics knows that the more frequently used action is actually written as integral of Lagrange, L, x dot, which represent the velocity. So that's the more recent one. Actually, the second form, this S, the action form, has been used by more people than other form. Here we also mentioned another form of action is W equal to the integral of the momentum multiply the coordinate Q, which is called the abbreviated action by Hamilton. And this W is related to the action S in this equation. So you have to consider a system where the energy is conserved. And you have to, the action is equal to the W, take the total energy, which is a constant, multiply the time taken. So this W is slightly different from the action defined by Lagrange. However, this action also is called it is called the action of the generalized coordinate Q. It's a general coordinate, could be the angle, could be the displacement in the position. And this integral is defined as action as well. Now, if you, this integral looks very familiar if you have studied the Bohr's original work on the atomic model. You can see that? So this is actually the quantum condition Niels Bohr proposed in 1923, that this integral, although they have relation to, although people interpret that integral in relation to the angular momentum, but actually from this information reference, you can see the integral is actually exactly the same as this so-called action of the generalized coordinate. And this is not surprising. Actually, the action can be written as different form. If you do some dimensional analysis, namely to find the unit of action, you will find that in many cases, the action, the dimension of action is joule multiply the time, or energy multiply joule multiply second, or energy multiply time interval. And this dimension is also equal to the dimension of the momentum multiply the displacement. In addition, the dimension of the action is also the same as the angular momentum. Furthermore, the dimension of action is also the same of the Planck constant. Interesting. So we're going to have some in-depth discussing in the future. But here I just draw your attention that the unit based on the study of unit of action, we can find some very interesting connections in different physical variables and also ideas. Of course, since the 1900s, since the 20th centuries, the idea of action has been adopted by many important physicists. Among the other things is Einstein. So the action in relativity can be written as Einstein-Hilbert action. So we just have a look at this form very briefly. So in a special relativity, the action can be written as negative MC. The reason we multiply this MC is just to ensure that the dimension or the unit is consistent with Joule and second. So this is action in the special relativity, and this is action in the general relativity. You can see this is Riemann tensor and curvatures. And this is how actually, without use this brief notation, that is how the relativity general Lagrangians in general relativity can be written as this form. And of course, in the special case, it just return to the special relativity. So we're actually talking about, this is a form we probably will discuss in the future. So the action in the special relativity is actually looking for the minimum, actually the maximum, should I say, the maximum local time. So this is tau is called the local time. And that is how action, or the least action principle, was used in developing Einstein's relativity. Perhaps I will also mention Richard Feynman's path integral in the context of the quantum field theory. And Feynman proposed that action is, in classical physics, can be rewritten as, considered as equivalent to the so-called path integral. So today we just give you a brief introduction. The path integral can be written as this form. So we still can see the trace of S here. So S represents is correspond to the classical form of action, but here is in the exponential form or logarithmic form, some people call it. And of course, this is some detail. How do we go to detail in order to invoke a sort of the green functions as Freeman Dyson proposed, and we can actually to write a more concrete form for the action in the quantum electrodynamics. Any other example? Propagate. So propagate is idea. We can go to detail when we discuss Richard Feynman's quantum electrodynamics. And the propagate is just a kind of the integral and in relation to the action. You see, so this S represents the action. Of course, action in this case is defined in the quantum field theory. So it's different, totally different idea. But mathematical form are similar. Here I will not go to detail. So that will be our discussing in the next video. I will just mention that why the action can be written as either as a product of the energy and the time, and also you can also write the action as a product of the momentum and the distance. So this is in-depth discussing in the future. I also would like to show you that the action idea has been continuously adopted in the modern physics research, in particular in the area of the quantum field and high energy physics, such as the standard model physics. But I would like to draw your attention that this is some detail about Dyson equation. Again, it is focused on the minimum, how to find the standing point or stationary point of this action, so that we can derive the equation of motion, or in this case, expectation of the measurable variable. We're not going to talk about this quantum field theory in detail. Okay, another important development in electromagnetism is that the discovery that the field, electrical field, can be properly described by introducing a proper Lagrangian. So this is a Lagrangian in relation to electrostatic field, classical one. In this case, the field was treated not necessarily as independent physical being. Rather, it's just the variation of certain quantities in space. So in this way, we can actually derive the Maxwell equation, or sorry, Gauss law. We can derive the Gauss law by using this least action principle. There is another one that is Lagrangian for point mass in Riemann manifold. That is general relativity. We're talking about the Lagrangian in the general relativity as well. And okay, let's talk about continue our discuss, give some more information about electromagnetic field. Okay, and since Maxwell united the electricity and the magnetism, it was accepted that the electromagnetic field can be described either as the wave in the media or just as a field in the vacuum. So no matter which way you look at this issue, the mathematical form in line with the least action principle are the same. So this is actually the Lagrangians for the electromagnetism. And in this case, and it's I just highlight this the last part. So the second part, the first part is associated with the charge and the current in space. But the second part is merely the property of field. So since the beginning of the 20th century, that more researchers in the field theory began to consider whether we should treat this electromagnetic field as a real physical being. And this idea was supported by the Michelson-Morley experiment observation, in which they failed to observe the presence of ether. So from the beginning of the 20th century, that electromagnetic field for the first time was treated as physical beings. So in particular, this abstract notation is called the electromagnetic tensor. Or by the way, by using Lagrangian, another beauty of the Lagrange's formalism is to allow the people to rewrite the Maxwell equation into this more compact form. So it's beautiful, it's simple, and in which that the this F tensor is called electromagnetic tensor, which contains the difference between the four potential. A is four potential. By definition, I think I discussed this four potential before that in the classical field theory. And so these four potential include the first components is ordinary electrical potential. But the last three components represent a vector potential. So if we just use the four, if we combine these the variable into a four-dimensional vectors, then we can obtain the four potential. By the way, it also appears, actually, its very important feature was discovered after Maxwell, that if we invoke these four potential, then we will see that under Lorentz transformation, and these four potential remain invariant. So that hence these four potential or the electromagnetic field as a whole is considered as the gauge invariance. So under Lorentz transformation, if the property or if the quantity remain the same in their mathematical form, and that property is treated or is considered as Lorentzian invariant or the gauge field. So that is the idea of the gauge field. Gauge field is just purely mathematical requirement to ensure that under the Lorentz transformation, that the mathematical form of the property of the quantity remain the same. Of course, this is another important idea. It's called Young Muse Lagranges. It is a mathematical field theory derived by the two physicists, Young and Muse, in 1954, in line with the argument that is under the so-called gauge transformation, then we should be able to derive the general form of Lagranges to study other interaction beyond the electromagnetic interaction. Actually, from this form, mathematical form, you can see this Lagrange for the Young-Muse Lagranges is identical to the field energy density appeared in the Lagrange for Maxwell equations, or the theory, the field theory, the classical field theory of the electromagnetic field. So that is one can simply consider the Young-Muse Lagranges is just a generalized the gauge field, which will take the Lagranges for electromagnetic field as a special case. So then in doing so, they have introduced different idea of symmetry or groups, so that of course they can treat when they treat this when they introduce the general groups, which is more general than the group used to describe the electromagnetic field, and then we can build this what we call the Young-Muse Lagranges. Of course, this is a big issue. Okay, this is because these Young-Muse Lagrange remain silent for decades before around the 1970s, when P.W. Anderson, so that's why I put this name here. And when P.W. Anderson introduced the idea of so-called symmetry breaking, and people suddenly realized, theoreticians, mathematical physicists, including Yang and Muse, realized that this is actually exactly, that is a good opportunity to actually to apply this idea of this gauge field theory. Okay, and of course, eventually this development eventually led to go to the final form or present form of so-called the standard model. So this is very important. So if you look back, you can this insight developed in 1954. Actually, 1954 was very important years. In 1954, it is also the year when Cuba, Tomita, generalized introduced a general linear response theory for the study of magnetic resonance. So that is the origin of this linear response theory. And of course, many things happened around 1954 and 1953 and 1954. However, I'm going to prepare a particular talk about this issue called "Is the Young-Muse field misleading in physics?" Okay, let me know if you are interested in this kind of topics, or you want to, or shall we discuss something else? Please let me know. All right. Okay. In passing, another important thing is that the least action principle was also used to explain the Dirac equation. You know, in 1928, around 1928, Paul Dirac first combined the existing quantum physics, which is a non-relativistic form, combined this non-relativistic form of quantum mechanics, namely the Schrödinger equation, with Einstein's special relativity. Dirac derived this Hamiltonian equation. So on the left hand is actually represent the energy. So people who for Dirac himself, he didn't mention, he just used this simple mathematical treatment, derived many important ideas, such as the spin of electron, the antimatter, the positron. And so this is a very important outcome from the Dirac's equation. But some people, if you look at this equation, you can simply argue that we can introduce what we call the Dirac Lagranges for the Dirac equation, because this term, can you see this is a wave function? So this term actually represents the expected value of energy. So bear in mind that important idea of the Lagrange's formalism is that to use energy. To be exact, the difference between kinetic energy and potential energy are the Lagranges. So therefore, this is straightforward if you accept that Lagrange can be built by using energy. So this is not surprising that one can introduce Lagranges for Dirac equation. However, more general form can be found if we just use the idea of the gauge invariant proposed in Young-Muse theory. Then we can also perhaps make these Lagranges for Dirac equation more general. And this is, so whenever you see this stamp, just like you go to immigration office, they get a stamp, oh, you can stay permanently. So whenever you see this stamp, gauge invariant, then you know that this form is more general and to the original form derived from the Dirac equation. This is something very, there are some relevant issues here we can discuss more. That is, whether the condition or the constraint of gauge variance provide the correct way to insert for more fundamental equation of motion of different interaction, or this is actually misleading approach. Because after all, there's another issues people haven't resolved, is that the divergency, the infinity, the divergency of the quantum integral dynamics, in particular from the quantum integral dynamics, and go to the other interactions such as weak and strong interactions. There's always an artificial approach one have to invoke that is called renormalization. Okay. So that is another issue. Whether renormalization is guaranteed by introducing the Yong Muse, the gauge field criteria. In other words, if the Lagranges satisfy the gauge, it became the gauge invariant. Does that mean that infinity or divergency automatically disappear without explicitly added some additional terms in order to avoid the divergency in quantum field theory? These are some of the basic issues we can discuss in the future. Okay, please let me know whether I should continue in this direction or added another issues I didn't include in this introduction. Okay. Okay. Thank you for reviewing, and please like and subscribe so that I can prepare more interesting video to explore and share these knowledges with more audience. Thank you and goodbye.